find it. All right. Is recording. Yeah. All right. So we were talking about curvilinear motion, right? We talked about Cartesian coordinates. We talked about normal tangent coordinate or tangent normal coordinate, any way you want to refer to it. And today I'm going to talk about polar coordinates. I just, again, remember that we are still studying the same type of motion. We are looking at the particle or an object moving on a path that is not a linear path, right? Moving on a curved path. That's the type of motion we're studying. We are just using different coordinate systems to study that, to study that specific motion. So this, hopefully I follow the right color code. This would be polar coordinate. Polar coordinate system. So we did two things. First, we used Cartesian coordinate system. We put x, y axis somewhere, and then we studied the motion of a particle. Right? Then second type, tangent normal coordinate system, or normal tangent coordinate system, was basically our coordinate system was attached to the point or particle we were studying, and we defined the coordinate system using two unit vectors, right? T and En. We said Et is the unit vector tangent to the path at the moment that we are looking at that motion, or a specific moment that we're studying the motion, and En is the unit vector normal to the path, or normal to Et. You can think about it this way, it's better. Normal to the tangent direction. And we said En is in the direction of concave. If you have a curve or you have a path, always En is pointing from where the particle is towards in a concave direction for that curve. Now, for polar coordinates, right? We also remember to define a coordinate system. We need to define unit vectors for that coordinate system. X, Y coordinate system is defined by I and J. Tangent normal we define that with E, T, and En. A polar coordinate system or polar coordinates, we define that using ER and E theta. We define two new unit vectors, and we use those unit vectors to basically formulate the same problem that we were studying. All right. So let's put it this way. Let's draw it here. Let's say I used to have an arrow there. There you go. Let's start with the coordinate system XY. That's the one we're familiar with, we're comfortable with, XY. And let's say I have my point P somewhere here. Right, this is point P, or particle, where the particle is with coordinate XY. Now, I represent that, let's say this is the vector representing a position of point P in XY coordinates. Let's call this R. And this is the angle theta, the angle that vector creates with the x-axis. So I'm going to define two unit vectors for this new coordinate system I'm trying to define to formulate or study this curvilinear motion. I define ER and I define E theta. ER being this way and E theta being this way. Let's see what they are. So ER, I'll say it points in the direction of the radial line from the origin, if this is the origin, let's say point O, to point P. That's where ER is. That ER is supposed to be aligned with, maybe it's a little, it's supposed to be aligned with R. So here's how I define ER. It points in the direction, let's say in the direction of the radial line from the origin to P, where that particle is we're studying. And just for the sake of completeness, you can think about this particle as part of some curvilinear path, or some path that the particle is following. And E theta is pretty much perpendicular to ER. That's what, right. So E theta is perpendicular to ER, and let's also add this, and points in the direction of increasing theta. Right. Theta is increasing in this case counterclockwise, so E theta is this direction. If it was increasing clockwise, E theta would have been downward, still perpendicular to ER. So that's how we define our coordinate system. Two unit vectors, ER and E theta, is enough to define our coordinate system. And remember, this is also attached to the point, similar to tangent normal coordinate system. So if we define it that way, then R, let's make, oh, this is a vector, just you know. I guess it's obvious the way I write it. So R, right, position, remember we're talking about three things: position, velocity, acceleration. That's all we care about at this point, in this, within the scope of what we're talking about right now. Right? Position, velocity, acceleration. So position in this coordinate system. So we define these three in any coordinate system that we come up with. Now we're in polar coordinate system. Let's define these three in polar coordinate system. Right? When we were in tangent normal coordinate system, we define these in tangent normal coordinate system. XY coordinate system, we define those in XY or XYZ coordinate system, if you want to go into the third dimension. So R, right? R would be R, the magnitude of R, whatever it is. I'll just represent that with R. ER, magnitude and direction. If remember, a vector has two things: a magnitude and a direction. R is being the magnitude, or the length of this vector, and ER is the direction. Right? That's how we define ER. ER is aligned with R. This being the you can write it this way: position vector from O to P. Position. Now we look at velocity. Right? Position, velocity, acceleration. Velocity. V. You just follow the definition. Velocity is a derivative of position with respect to time. We define it all the way at the beginning, pretty much. So V is d. I can define it. D R dt. This is supposed to be R. I don't know how much close I got to R. dr dt. To take derivative with respect to time from a vector, as I said, you have to, this R as a vector is basically R multiplied by ER, so the multiplication of two quantities. You can think about it that way. So the derivative of multiplication is derivative of the first component multiplied by the second component plus derivative of the second component multiplied by the first component. So dr becomes dr dt ER plus R d ER dt. Now, without proving like what I did for tangent normal, I'll just tell you, you can take a look at your textbook and see probably a more detailed proof of that. dER dt becomes theta dt e theta. And in similar way, you can also prove that dE theta, we don't really need it here, but just, dE theta dt is equal to minus d theta dt er. Now, again, I'm not proving this. Just keep that somewhere. You probably, I believe, if you take a look at your textbook, you'll get a better procedure how to actually prove this. Where do they come from? But just take it from me. It's at this point it's irrelevant to what we want to get. So if we do this process, der dt, well, it becomes d theta dt e theta, right? So I'll just replace what I got there. This becomes dr dt er plus d, I should not forget r there. R is the bank. So r d theta dt e theta. That becomes the relationship for velocity. Now you can write it in a probably more like easier way, I would say, not easier way, more convenient way. Remember, we defined d theta dt as omega. If you remember when we were defining angular velocity, right? We said d theta dt can be defined as omega, or you can look at it as theta dot. It's the same thing. Theta dot here being the derivative with respect to time. So I'll just write here dot is d dt. Wherever I use dot means derivative with respect to time. So if you follow that, you want to represent d dt with dot, you can represent dr dt also with r dot. So at the end of the day, here's what you get. You get v is equal to let's just write it in this way first. dt er plus r omega e theta. Or you can write it as r theta, r dot er plus r theta dot e theta. All the same, pretty much. Take derivative with respect to time from position. That gives you the radial component of velocity, and find r multiplied by omega. That gives you the theta component of your velocity. So remember, now just pay attention that when we were talking about one difference you will notice here between polar coordinates and tangent normal coordinate is that in tangent normal coordinate, velocity was always in the direction of tangent. Right? Velocity had only one component, and that component was ds dt. If you remember, it had one component, and that was along tangential direction. Now in polar coordinates, your velocity has two components, one in radial direction, one in theta direction. So this is one thing to remember. This is the velocity. Position is not, I'll just draw it here in case you're following position, velocity, and then acceleration. Right? Acceleration, you can take derivative with respect to time. That's a little longer. You take derivative with this v with respect to time. That will give you acceleration. I'll just give you the final form, right, instead of going through. The second form that I put here, the second expression I put here, right there, that'll actually come handy when you are trying to simplify the derivative with respect to time from velocity to get to the expression for acceleration. If you do that, move things around, again, I don't see any benefit of me going through it, the process for you. Probably you're just going to see it once and once, I would say forever. So you don't really even need to know how to get there. But take a look at your textbook. You'll see a more detailed process how to get there. So that'll be, if you do that, it'll give you, It will give you, let me write it this way so we can separate the components. What is wrong with parentheses that I'm trying to use? Oh, let's use this because I want to use parentheses. So second derivative with respect to r dr dt second derivative minus r d theta dt, this is t squared. This becomes your component in r direction or radial direction. And the second component or component in theta direction is r second derivative with respect with respect to t or time from theta plus 2 dr dt d theta dt e theta. Right? It's relatively long, but we can actually use our notations and write it in a, I would say, better way, right? Or easier to, I guess, copy, I would say. Dr dt, well, you can write it as r dot, let's d, let me follow the color code I've been using at least in one page. R dot d theta dt, right? It's basically omega or theta dot. Second derivative, you can write it as alpha. Remember, angular acceleration was the second derivative of theta with respect to time, or derivative of angular velocity with respect to time. So I can write it alpha or theta double dot. I'm building on what we defined from before. Second derivative with respect to time for r, you can think about that r double dot. So let me actually add it here in case later on you look at your note, you just know where does this come from. I'm just saying double dot is second derivative with respect to time. Keep this here. Later on when you look at it, things are not weird suddenly. And this again is omega or theta dot. Now if I rewrite this again to get a better form, I would say sometimes easier, not sometimes, a lot of time it's easier to follow this instead of writing d dt second derivative with respect to time. It's probably easier to just write a is equal to, that'll give you, I forgot, gives you r double dot minus r theta dot squared, right? R double dot minus r theta dot squared er in radial direction plus in theta direction r 2 r dot theta dot plus r theta double dot. If 2 r dot theta dot plus r theta double dot e theta. And again, you can still write it as r double dot if you're more comfortable with omega as we define it. Omega and alpha, you can write it as r double dot minus r omega squared er plus 2r dot omega plus r alpha e theta. We double check it, I didn't make a mistake. 2r dot omega plus r alpha. I can write a bit r alpha there. R alpha, yeah. R alpha. So here is what you get for acceleration. Pretty long. But keep in mind, two components. By the end of the day, V has two components. All right, let me just. V has two components. VR ER plus V theta E theta. And A also has two components. AR ER plus A theta E theta. Right? And VR is pretty much just R dot, and V theta is, I forgot that, R theta dot. Right? R theta dot. I'm just rewriting the same equation over and over pretty much, writing in different forms. Right? AR being R double dot minus R omega squared, A theta being 2R dot omega plus R alpha. So in polar coordinate system, your velocity has both components in R and theta directions, as opposed to what we had in normal tangent system or tangent normal coordinate system, where our velocity had only one component and it was in tangential direction. Right? We just, again, representing the same motion in a different coordinate system. Acceleration has two components. Components here are longer than what we had before in tangent normal coordinate system. Here, AR becomes R double dot minus R omega squared, and A theta, which is in theta direction, is 2R dot omega plus R alpha. Right? Now, you might ask that why do we keep switching from one coordinate system to another, or why do we need to know different coordinate systems? Now, this is more about convenience, right? Depending on the problem you're dealing with, one coordinate system makes your life easier compared to the other one. So if you want to go with X, Y, so all the problems you deal with theoretically can be solved with all these three coordinate systems. Right? But the difference between the solution can be huge depending on what coordinate system you're going to use. So it's more about which one is going to make your life easier when you're dealing with a problem or a motion on a curvilinear path. Right? The motion is the same. You decide what coordinate system should be used to make it easier to get to what you want, to find the unknowns, to solve the problem, to deal with that engineering problem that you have to deal with. Right. Now, as a matter of fact, there are so many cases, especially between polar coordinate system and tangent normal, that the problem can be solved with both. I would say good number of cases, it's pretty same level of, I don't want to say difficulty, whatever word you want to use. Both coordinate systems work fine. Right? Not always, but in so many cases, you can actually use both, depending on which one you feel more comfortable with. X, Y, I'm hesitant about that, except when you're dealing with projectile motion. Probably XY coordinate system is not specifically the best coordinate system to deal with curvilinear path motion. But tangent normal and polar coordinates, in so many cases, can be used both. All right, so let's also take a look at how to go from one to another. I guess that's something that we talked before. So let's say a relationship between relationship with, I'm going to provide it this relationship with Cartesian coordinates. And I'll also mention the relationship it has when we talk about briefly circular motion this coordinate system has with tangent normal. So if I have my, let's say, coordinate system right there, x, y, this is x, this is y, and you have your I and J, I and J, and let's say you have a point somewhere here, my point P that we were actually studying, and then you have that, and then you have your theta there. There you go. And then this is going to be your ER and E theta. This is ER, this is E theta. Now you can think about it this way. If I put I right there and J right there, this angle being theta, hopefully you can see what's going on there, this angle being theta, I can write ER being I cosine theta, or I can just write it cosine theta I plus sine theta J. In this triangle there, let me see if I can draw it here. This is ER, this is theta, this is I, and this is J. So if I want to find the components along ER, this is one thing I look at. This is I cosine theta I, and then I don't want to make it crowded there. Probably already did. And then this one is going to be sine theta J, because this is theta as well. Yeah, I don't know if I helped the case by just making it from there. But pretty much as right triangle, you project I and J, you find the component of I and J along ER, and then you just pretty much that gives you the conversion. Same story you can do for E theta, right? For E theta, you're going to get minus sine theta I plus cosine theta J. You can do it the other way as well. We can find I and J from ER and the E theta. You can find I. That's just playing around with triangles and how to find the, let me write it here. I is ER cosine theta, or cosine theta ER minus sine theta E theta. Minus sine theta. Actually, this is a good practice if you look at it later and make sure that you get the same thing playing around with triangles, an angle. And J becomes ER sine theta, so sine theta ER plus E theta cosine theta, or cosine theta E theta. A lot is going on there. Just for each conversion, you have to draw the triangle. If, for instance, if you look at, let's say this one, we want to find I, right? So this is ER, this is E theta, and there goes I. This is angle theta. This is also angle theta. Now in this case, you look at this triangle there, right? So this becomes ER cosine theta. The ER on I direction, in I direction becomes ER cosine theta. And in J direction, it becomes ER sine theta. You have to look at this triangle right there. This is E, and it's in the negative direction, so it becomes E theta sine theta. This one is projected right there. becomes ER cosine theta. Now ER sine theta is in the negative side, so it becomes ER cosine theta minus E theta sine theta. I'll leave the rest to you to play around with them and figure out how this conversion works. All right, so just to prevent everyone from getting lost where we were going, we defined a new coordinate system, ER and E theta. Right? We started looking at three quantities we are always interested in, three vectors, I would say. Position, velocity, acceleration. Position was easy to define. We said, well, as long as we know the length and we know where the point or particle is, the component would be in ER direction, radial direction. Velocity, we took derivative. The rest is just math. Right? The simplification, the process, everything is just math here. There is not that much going on in terms of defining what we had from before. The only thing that happens is that now velocity has two components, one in r direction, which is r dot, or the derivative of r with respect to time, and one in theta direction, r theta dot, or r omega, since we define theta as omega. Acceleration, take derivative with respect to velocity. Now, equation becomes much longer. You have one component in radial direction, one in theta direction. Now, the radial direction itself is r double dot minus r theta dot squared, or r omega squared, and in theta direction you have 2r dot theta dot plus r theta double dot, or 2r dot omega if you want to represent theta dot with omega and theta double dot with alpha, which we defined before, angular velocity and angular acceleration, right? Here omega is angular velocity, alpha is angular acceleration. So we're not doing that much except taking derivative, pretty much. And I said the relationship with Cartesian coordinate system, you basically decompose ER and E theta along I and J, or the other way around, decompose I and J along ER and E theta. Last thing I want to talk about this coordinate system before we start looking into examples is circular motion, right? We said circular motion is a special case when we have a particle moving on a curve. Right? So curvilinear path is general path, but in a special situation, that path could be a circular path. So that basically simplifies our equations a little bit. Why? Because R, as the position, is not going to have any derivative with respect to time, right? Because when you are in a circle, write it here, circular motion. When you are in a circle, the radius is constant, so it does not change during the motion. You're not going to have any R dot if this is the center, and let's say I am totally losing the colors there. So let's say P is here, P is here. That'll give you ER, and let's call this R. This gives you ER. This gives you E theta perpendicular to R. And you can think about this as theta. So R is constant now. So as a result, there is no R dot would be 0. R double dot also would be 0 in all those equations. So if you go back to the equation for velocity, what was the equation for velocity? The first term right here and the second term. Component in VR and ER in the direction of radial direction was R dot, so that's 0. Component in theta direction is R theta dot. Well, we represent theta dot with omega, we can represent that. R, lowercase r, is now just fixed, and that would be the radius of your circle. So your V becomes R omega E theta. Or we can represent that with R theta dot E theta, whichever you feel more comfortable with. Right? So it's a special case for the motion on a curvilinear path when we're talking about circular motion, motion on a circular path. Your acceleration, right? If I go back, if I can go back, okay, there you go. Your acceleration, well, the R component of acceleration, or AR, I'm talking about this one. R double dot is 0, right? R doesn't change in a circular motion. Lowercase r becomes uppercase r, so it's the radius. So AR becomes minus r omega squared. So your acceleration becomes minus r omega squared ER in radial direction. In tangential direction, right there, r dot is 0, so the first component is gone. The second component stays there, and lowercase r is basically just the radius of your circle, so it becomes r alpha. So this becomes r plus r alpha E theta. Now let's see if I can explain this without making it confusing. Remember tangent normal coordinate system. Right? In tangent normal coordinate system, this would have been ET, this would have been EN, or this is EN, if you're studying the same motion using tangent normal. So this is polar. In tangent normal, or normal tangent coordinate system, here is what we had, if you remember. We had V was VET, basically velocity ET. And we had acceleration as dV dt ET plus V squared over R E N. Or this could be R omega squared. See what happens. So tangent and theta are pretty much telling us these two are equivalent in these two coordinate system, if you want to think about it this way. So ET and E theta are overlapping. And EN and ER are the same but in opposite direction. The line, they're collinear but in opposite direction. So your EN, the component, normal component is R omega squared when you're using tangent normal coordinate system. But when you're using polar, it's minus R omega squared. That's something that you can probably distinguish easily. I just wanted to mention that, again, same motion, different coordinate system. In a circular motion, this happens. EN and ER basically are in opposite direction. This is not general though. In a curve, these two have very different, formulation obviously, and the different way to deal with, because ET is always tangent to the path, so it changes. ET and EN, they change, but ER and E theta, ER is always along the radial direction, connecting wherever the point O is in our coordinate system. All right, let's look at these two examples. To just clarify things a little bit. I gave you a lot of equations there, and let's see how can we actually use them. Let's look at the first example. Question on what we did there. Does this, hopefully it makes sense. If it doesn't, in terms of what we did and what is the general story, tell me right now before we start looking into examples. Right? Examples, we'll see how we can actually implement these for equations and how can we actually use this to study the motion on a curvilinear path or circular path, depending on what kind of path you're dealing with. But the story is, again, pretty straightforward. Same motion, different coordinate system. Right. Let's look at the first example. We have a color there. Let me see if I draw this. I have this is fixed right there, and then we have this one like this, and then this is and this fixed right there, and I'll make the color here. So that's just basically a rod. This is a color that can slide on this rod, going back and forth this way, either this way or this way. So it can slide on the rod, and that rod is connected to this point, and it's rotating. Let's say in this direction, for instance. You can rotate either direction. Let's call this A, this color A, and the distance it has from here as represented with R, and then here is our theta. So what happens is that this rod rotates around point O, we call it point O, and at the same time this color can slide on the rod. So we have two things going on, this rod rotating and the color going up and down on the rod. All right, that's the system. Now, what we are trying to find out, here is what we're given. We are told that the polar coordinates of the color A are given as functions of time in seconds by R being 1 plus 0.2 t squared and theta being 2t radians. Now we're asked to find what are the magnitudes of the velocity and acceleration of the color at t equals to 2 seconds. All right. We are asked to find, well, if you want to think about your polar coordinate system, this would be your ER, this would be your E theta. That is something you have to be able to identify. Right? When you're given something like this, you have to be able to identify, well, this is R, radial motion, so ER should be in that direction. Assuming that the motion is counterclockwise, E theta is in this direction. As long as we get the E theta perpendicular to ER, it should be fine. In this case, yes, go ahead, Sam.
Sorry, quick question. Does it matter where you put the coordinates in terms of ER and E theta? Like if you put it where you put it now or like on the edge of the rod?
No, so ER and E theta should be always attached to the particle that you're studying.
Okay.
All right. So similar to E theta, ET and EN, but ET and EN were basically connected to the path somehow. Like wherever the particle was going, if it was the case like this, you were following the particle, but you're also following the rule that ET is tangential and EN is, well, in this case, is in this direction. And if you are here, this is ET, this is EN. So you always follow the point you are studying. Now, in terms of ER and E theta, wherever your origin is, let's say your point, the point O is here. And this is your X, Y, if you want to think about it. For that, it all depends on where you are. So if, I wanted to show the difference, so let me move it a little in a weird way, like here, X and Y, and this is O. Then this becomes your R. So as a result, this is your ER, if the point is here, and this is your E theta, assuming that at the moment you're going in this direction. In the second point, if you still follow the same particle, when it's here, this is your R. So as a result, this becomes your ER, and depending on at the moment which direction you're rotating, let's say in this direction, this becomes your E theta. So in radial or polar coordinate system, always look at position vector. Along that direction is your ER, perpendicular to that is E theta. Now at the moment, depending on which direction theta is increasing, you decide which point E theta should, which direction E theta should be pointing. E tangent and E normal, you don't care about any X, Y, or origin. You just stick to the point and say, well, at this, when the point is here, the particle is here, tangent to the path of its direction is ET, normal to the path of its motion is EN. Now, EN is pointing towards the curvature. Right? I didn't really do a good job drawing EN here. Depending on if the curve is this way, EN pointing in concave direction. If it's the path is like this, EN pointing this direction, concave. So this is there is a get a sense of polar coordinates and tangent normal. Don't get these two confused, right? They both are attached to the particle, but the way they are defined is different. So hopefully this is straightforward. A velocity with r dot er plus r theta dot e theta. So we just follow the definition. All right, it's just math. R dot, well, derivative with respect to time. We are given r. If I take derivative with respect to time, it becomes 0.4t. Theta dot, the only thing I need, I guess, is theta dot. Theta dot is 2. So we can replace these. So V becomes r dot, which is 0.4 TER, plus r, which is 1 plus 0.2 t squared, theta dot, which is 2, E theta. You can probably write it better. Let me just put it together, multiply it by 2. This becomes 2 plus 0.4 t squared E theta. Does that make sense? I basically just use a definition for V right here. Right, you can either there or here. I basically follow the definition for V. R dot ER R theta dot E theta, or R omega E theta. So that gives me the expression for velocity. Now I'm told to find it at t equals 2 seconds. So at t equals 2 seconds, we just plug in V at t equals 2. And that becomes 2 times 0.4. So this becomes 0.8 ER plus 4 times 0.4 1.6 plus 2, 3.6. 3.6 e theta. This is velocity at t equals 2 seconds. Now this is represented in polar coordinate, right? If you want the magnitude, what do? Can someone tell me how can I find the magnitude of the velocity? This is represented in polar coordinate, er and e theta.
Would you take the square root of 0.8 squared plus 3.6 squared?
Exactly. Thank you, Anna. Pretty much this is a coordinate system, right? Like any other coordinate system that you have. If you have components, this is er, this is e theta. If you have a vector there that you know its components, if this is vector v, and you know that this is vr and this is v theta, right? Vector v. The magnitude of the vector is basically just the square root of summation of squared of its components. So v, the magnitude, I'll represent it this way, is the square root of 0.8 squared plus 3.6 squared. Let's see if I have the number for that. It should give you 3.69. Units are given here or no? R. Actually, the unit apparently is foot. So that becomes foot per second. Now, the magnitude is the same. It doesn't matter what coordinate system you use. If you use tangent normal, you're still going to get the same magnitude. Yeah, the components would be different. Your component in ET and EN directions are going to be different, but the magnitude of the velocity by the end of the day should be the same. Doesn't matter what coordinate system you use, because coordinate system are just representations. The magnitude of velocity should be the same. Keep that in mind. No matter how many times you switch the coordinate system, the magnitude is the same. In this case, I have to look into it. Maybe you can still change. The easiest way is polar coordinates since you're given r and theta. I don't think in this case you can solve it with tangent normal. Right. Now, that was velocity. I also asked about acceleration. So A is AR ER plus A theta E theta. All right. It's easier to just separate them since it's a long equation. AR was R double dot minus R omega squared, or R theta dot squared. Let me write it. I'll just write it this way. Now here's what I need to find now. I need to find R double dot. So let's find it here. I'm going to write it in this corner. R double dot is second derivative with respect to R, second derivative of R with respect to time. Well, one derivative will become 0.4 t, and the second one becomes 0.4. So that's R double dot. Well, omega is basically just theta dot. We already found that it's 2. So I'll put it here. I'll just did some recalculation there. So this becomes 0.4 minus R, which is 1 plus 0.2 t squared times omega squared, omega being 4. Let me just put 4 in the back. Let's just keep it that way so later on you can follow what's going on. A theta, let's shorten this. A theta was 2r dot omega minus plus r alpha. We know r dot, we know omega, we know r, we don't know alpha. So let's find alpha. Alpha What is alpha? Angular acceleration.
Isn't it theta double dot
Which becomes
0?
0. Exactly. Thank you. Becomes 0. So the first component is gone, right? Through out of the window, pretty much. The second component, right? This one is gone. The second component is gone, sorry. The first component becomes 2r dot omega. R dot, I know, is 0.4. 2 becomes 0.8. Omega, sorry, 0.8 t. 2 r dot, yeah. And then omega, whatever is omega. Omega is 2. 2. So you get A, your acceleration vector, as, clean that up here. I don't know why I'm writing A. So your acceleration vector becomes 0.4. I'm going to look at my, you know what? Let's just do it at time 2. Oh, let me just not skip direct step. So A becomes 0.4 minus 4 plus 0.8 t squared ER plus 1.6 TE theta. Right? That becomes the acceleration. If I'm not wrong, 0.4. Yeah. And you can calculate. Go ahead. Sorry.
I was just gonna say, shouldn't that be a negative?
Did I miss something? Yes, it should be. Thank you. That should be negative here. That minus comes into parentheses. There you go. Thank you. And pretty much just plug in the time t. Right? And I'll just put it this way. At t equals to 2 seconds, your acceleration becomes that. I can give you the number. Minus 6.8 ER plus 3.2 E theta. This becomes your acceleration at t equals to 2 seconds. The same story, you can find this magnitude. Again, it doesn't matter. I'm scrambling things here. The magnitude of A, right? I don't write it there. So minus, it becomes the square root of minus 0.6 squared plus 3.2 squared. If you do this math, you will get the magnitude for acceleration. I can give you the final number at least. 7.52 foot per second. This is the magnitude of velocity. This is the magnitude of acceleration.
Wouldn't a union be like phi over x squared? But the magnitude of acceleration.
Magnitude of acceleration. So it's going to be square root of 6.8 squared plus.
The unions is not right. Yes.
I don't know which part you mentioned. Can you give me a better address to which part of what I wrote? So I'm looking at. Oh, I see what you're saying. Yes, second square. That I get, but I don't know, mention which part you were.
No, I mean that I understand this. I just the unions got picky a little bit.
Oh, okay, units. All right. Okay, but that was the same problem. Yeah, I'm not the best person, the most meticulous person when it comes to units. Not a good habit though. You'll never follow that. Um, you can always look at me as the example that you shouldn't, something you shouldn't be in terms of putting units. I could have been probably one of those people who causes a lot of damages to an engineering firm by mixing up units. Uh, all right, so you get the magnitude of velocity and acceleration. And again, I'm going to emphasize the magnitude should not change from one system to another. In this case, the only possible way, the way they phrase the problem statement is to just use polar coordinates. Now, let's look at another example. Uh, let's look at this one. I have something. A question on this one. Okay. Does that make sense what they did? All right. As long as you get the coordinate right and remember where is ER, where is E theta, where is ET, where is EN. Well, that's for tangent normal. But I know later on these two are the ones that can be mixed up. So that's why I keep bringing up tangent normal along with polar coordinates to make sure that you understand the difference. And the rest is just a bunch of equations and finding out the parameters. All right, so next example would be we have again our coordinate system there, x, y. This is x, this is y, and we have point P there. This is here, and let me just write the problem statement first. The radial line rotates with a constant angular velocity of 2 radian per second. Point P moves along the line at a constant speed of 4 meters per second. All right. Now you're asked to find the magnitude of the velocity and acceleration of P when T is equal to, oh, not T in this case, when R is equal to 2 meters. So here's what we have. This point is rotating with 2 radian per second. Its angular is radial velocity is, let me put it right here, is 4 meters per second. And obviously this is your R. And here is your origin of. All right. Now let's start. We want velocity. So I'm going to write down the equation for velocity, R dot ER plus R theta dot E theta, or omega E theta. Let's figure this out. VR is equal to R dot is equal to, how much is R dot?
Would it be 0 in this case?
Well, look at the figure. So what is direction of r? Well, let's see. So we have angular velocity of 2 radian per second. And we know that point P moves along the line at the speed of 4 meters per second. So r dot is dr dt. Right? The change of r with respect to time. Now, this change of r, we're just talking about the change of length, right? The length of r. Remember, er, the direction of that is added to it by er. We are just looking at how is the magnitude of r changing, how fast is changing, what is the rate of change of r. Remember, this is r, right? This is where your point is, P. And forget about the theta component. If this is r, direction, this means that whatever is velocity in r direction would be your VR. Right? VR is r dot is dr dt. Because that's what you have in ER direction. This is ER direction. So when you're told that this point moves along the line at a constant speed of 4 meters per second, it means your r dot is 4 meters per second. You can think about this as just the motion of a straight line. Forget about E theta at this moment. You are just looking at the change or rate of change, how fast r is changing. And that would be just r dot. And that's basically how fast the point is moving along the line, along the radial direction. And it's given as part of the problem statement. Hopefully it makes sense. Now, once you get comfortable with that, then V theta is basically R theta, theta dot, or R omega, the way you want to write it. That's, okay, so what's that?
Would it be just 2r?
2r, so 2 times R. Yeah, let's just write it in general form. And technically, we know R is also 2, right? We want to find it at this point. So I'll just put it, plug in right here. So it gives you 4. This, if you, let's not put units there, things get confusing. I keep it to speed out the unit. So once you know VR and V theta, or R dot and R theta dot, you can just, you basically know your velocity, right? Your V is 4ER plus 4E theta. And as a result, we can find the magnitude, right? Square root 4 squared plus 4 squared, square root of 32, whatever it is. I actually don't have that number. You do the calculation. The unit for this is meter per second. Just keep the units that way. Things are not confusing. I might have the number. Hold on, so you can double check. Do have it actually. As a matter of fact, it becomes 5.66 meter per second. Once we know velocity, let's get into acceleration. Right? The same story, acceleration. I just write the equation r double dot minus r. What was that? R double dot minus R omega squared ER plus, let me double check the equation. 2R dot omega plus R alpha E theta. I can find the components there. A, if this being AR, this makes things a little more organized, and this being A theta, and this was VR, this was V theta. So you know where things come from, where they come from. AR, now R double dot minus R omega squared. What is R double dot? I remember, how did we figure out R dot? We said R dot was basically the velocity along radial direction. So following that logic, what is R double dot? I'm looking at the problem statement.
0.
It is 0, correct? Thank you. Yes, because specifically mentioned here that along the line at a constant speed of 4 meters per second. So R double dot is 0. I'm just going to put it here. It means R double dot is 0. Minus. Well, we're looking to find the acceleration at R equals to 2, so I'll put 2 here. And what is omega?
Would it be 2?
It's 2, exactly. Right. It's just specifically, explicitly mentioned, angular velocity of 2 radian per second, so 2. So this becomes minus 4. Sorry, it's 2 squared, right? So this becomes minus 8. A theta is 2R dot omega plus R alpha. Right? We know 2 is there. Well, R dot, we figured it out from the first part. It was 4. Omega we know is 2 plus R is 2. Give me 1 more minute, folks, to just wrap this up. I'm sorry, I know it's already 9. 2 times alpha. Okay, what is alpha?
Would it also be 0?
It's also 0, right? Because we're told that it's constant angular velocity. So I'll put it here. Constant angular velocity means alpha, which is d omega dt, is 0. So that's also 0. 2 by 2, 4. 4 by 4, 16. So from these two, you can find acceleration as minus 8 ER plus 16 E theta. And you can find the magnitude of acceleration as minus 8 squared plus 16 squared. That'll be 17.89 meter per second squared. Did I put meter per second there? Yeah. So here's what we were asked to find. This is velocity. This is the magnitude of acceleration. All right. Thank you for waiting for me. Yeah, we already passed time. So let me stop recording.